In this session, I talk on equi-energetic graphs with respect to the distance metrics. This concept energy, which is a parameter linked with molecules in chemistry, from the very beginning of that basic science, got its first connection with the graph spectrum through the works of E. Huckel in 1931. Huckel, in that paper, approximated the pi-electron energy of conjugated molecules by a linear relation with the adjacency eigenvalues of the graph of the corresponding molecule. This notion of energy further extended to all graphs by Gutmann in 1970s as a sum of the absolute values of the eigenvalues of the adjacency matrix of the graph. And in tune with this, in 2008, Vijay Kumar, Gutmann and myself extended this notion to distance metrics of a graph and defined the distance energy of graphs. And a testimony to the motivation of this definition of distance energy was established by Roberto Todeschini and Consoni in the very next year, where they proved that this parameter distance energy is a molecular descriptor as the best univariate models for the motor octane number of the octane isomers and the water solubility of polychlorobiphenyls. Another attestation of its academic interest is marked by around 202 citations of this paper on distance energy from 2010 till date. When the theory of graph spectra emerged in 1940s, in the very beginning of 30s, 1930 to 40, 10 years, through the fundamental work of Huckel. See, it was believed that non-isomorphic graphs have non-identical spectrum. Of course, identical isomorphic graphs have the same spectrum. So it is believed that non-isomorphic graphs have non-identical spectrum. And in this paper, in 1957, Kollatz and Sinkowitz produced a pair of non-isomorphic graphs with identical spectrum. And actually, this is the first mathematical paper concerning with the graph spectrum. And such graphs were named as co-spectral graphs in literature later. And it was again believed that only co-spectral graphs have the same energy, and which was disproved in the late 70s, and thus proved that energy is not a graph invariant, at least in the class of non-co-spectral graphs. This then led to the construction of equi-energetic graphs with respect to the adjacency matrix. And in 2008, when this notion was extended to distance energy is a concept concentrating on the graph structure in more detail than the mere adjacency matrix. We expected that the distance energy may be a graph invariant in the class of non-co-spectral graphs. And on the contrary, we were able to produce several classes of non-co-spectral, non-isomorphic graphs with equal distance energy. This distance energy being a molecular descriptor that finds application in designing medicines and thereby in pharmaceutical sciences. A more advanced problem regarding this distance and equi-energetic graphs is which distance equi-energetic graph is structurally simple is a problem yet to be addressed. And in this talk, we discuss such classes of equi-energetic graphs with respect to the distance matrix. We give several families of distance equi-energetic graphs arised from different kind of operations on graphs. And we follow these definitions. Let G is always a connected graph, and the distance matrix of G is a P by P matrix where P is the order of G and Dij is the distance between V and Vj. And the eigenvalues of the distance matrix of G are called the distance eigenvalues, d eigenvalues of G, and they constitute the distance spectrum. And two graphs G and H with identical distance spectrum are called cospectral, d cospectral. And the distance energy of G is defined as the sum of the absolute values of the distance eigenvalues. And two, so in fact, cospectral, d cospectral graphs have the same distance energy. And two non-d cospectral graphs with the same distance energy are called d equi-energetic. Naturally, when this concept was materialized, the natural question is whether which standard graphs are distance equi-energetic. So usually we check for paths, complete graphs, etc. But since there are unique graphs with n vertices which are paths and complete graphs, we dismiss the case of finding distance equi-energetic graphs in those family. And then the next standard graph appears to be the complete bipartite graph KMN, which in turn is the join of two graphs. One is a completely disconnected, a completely isolated graph on m vertices and the other on n vertices. So to find the distance spectrum and distance energy of complete bipartite graph, first we consider, we proved this theorem, the distance spectrum of the join of two graphs. And this was published in Applied Mathematical Letters, distance spectrum and energy of the composition of regular graphs, with Stevanovic and myself. And if Gi be an Ri regular graph with ni vertices and eigenvalues of the adjacency matrix are these: lambda I1, which is the regularity, lambda I2, etc., lambda In, then the distance spectrum of G1 join G2 consists of these eigenvalues minus lambda Ij minus 2 and these two numbers. So that the distance spectrum of the complete bipartite graph can be easily written from the adjacency eigenvalues of the complete bipartite graph. The complete bipartite graph KMN has adjacency eigenvalues plus or minus square root of Mn and 0 m plus n minus 2 times. So substituting these in here, we can find the distance energy of the complete bipartite graph KMN is equal to 4 into m plus n minus 2. Surprisingly, it does not depend upon any particular eigenvalue of KMN, but only on the parameters m and n. So for constant m plus n with m and n greater than or equal to 2, the complete bipartite graph KMN can provide a family of distance equi-energetic graphs. And this family, this is a family of distance equi-energetic graphs from the complete bipartite graph. For n greater than or equal to 4, we have k2 n minus 2, k3 n minus 3, etc. K floor function n by 2, upper n by 2 forms a family of distance equi-energetic graphs. And more precisely, if n is a given positive integer greater than or equal to 6, then let p1, p2 and q1, q2 be two partitions of n into two parts of size at least 2. Then k p1, p2 and k q1, q2 are distance equi-energetic. So for example, when p equal to 6 and 3 plus 3 are two partitions of 6 into parts with at least size at least 2. So 3 plus 3 and 2 plus 4. So these two are two partitions of 6 into two parts each of size at least 2. So by this result, we have k33 and k24 are distance equi-energetic. And this is a set of 4 complete bipartite graphs on 10 vertices. K2 8, K3 7, K4 6, and K5 5. So complete bipartite graphs provide a family of distance equi-energetic graphs for constant m plus n, for varying values of m and n, but with constant m plus n. And another family of distance equi-energetic graphs from the join appears to be the complete multipartite graph Km by 2 m by 2 join Kn by 2 n by 2. Here also the distance energy depends upon the sum m plus n. So for constant m plus n and for varying m and n, we have family of distance equi-energetic graphs from this. And this is one such family, K22 join Kn minus 4 by n by 2, n minus 4 by 2, K33 K n minus 6 by 2, n minus 6 by 2, etc. for n equal to 40 greater than or equal to 12. And these are 2 examples on of the complete multipartite graphs equi-energetic on 12 vertices. Another class of equi-energetic graphs obtained from the join operation is again Cm join K n complement, cycle join K n complement. And we have this family of distance equi-energetic graphs with n on n vertices with n greater than or equal to 7. All these graphs are equi-energetic graphs obtained from the join of 2 graphs. And another class is Cm join Kn by 2 n by 2. I have energy 4 into m plus n minus 4 for m and n greater than or equal to 4. And for even n and odd n, we get 2 distinct families of distance equi-energetic graphs. C3 join Kt minus 1 t minus 1, C5 join Kt minus 2 t minus 2, etc. is one family for n equal to 2t plus 1 odd for greater than or equal to 9. And another family is C4 join Kt minus 2 t minus 2, etc. for n equal to 2t greater than or equal to 10. And the list continues. Equi-energetic family from the join Cm join Cn, cycle Cm join cycle Cn, and C3 join Cn minus 3, C4 join Cn minus 4, etc. Ck join Cn minus k with n greater than or equal to 8 for k from 1, 2, 3, etc. floor function n by 2 is a distance equi-energetic family. And these are 2 examples, C4 join C6 and C5 join C5. And in our fundamental paper on distance energy appeared in Match in 2008, we proved that for every p congruent to 0 mod 6, for every 6 p equal to a multiple of 6 greater than or equal to 18, there exists a pair of equi-energetic regular graphs. The graphs so far constructed are need not be regular, and the existence of a pair of d equi-energetic regular graphs on every p equal to 60 with the 60 greater than or equal to 18 is proved in this paper. And we prove this by considering these arguments. So given p equal to 60, let G1 and G2 be the new non-cospectral standard cubic graphs on 2t vertices. The standard cubic graphs we consider are, one is K33 and the other is the non-bipartite graph. Sorry, the bipartite graph. This one is the non-bipartite graph. Non-bipartite graph. Sorry, the one is this K33 and that is this, and the other is the non-bipartite graph. This. If you consider these 2 graphs G1 and G2, which are non-cospectral. They are non-cospectral. In fact, one is bipartite, the other is not bipartite. On 2T vertices, with I give the example for T equal to 3. Then form the line graphs LG1 and LG2, which are 4 regular and on 3T vertices. And we can find that the positive d eigenvalues of their join LG1, the spectrum of LG1 and LG2 can be obtained from the adjacency spectrum of G1 and G2. There is a classical result that the adjacency eigenvalues of LG1 and G1 are related by lambda I plus r minus 2. If lambda I is an eigenvalue of G1, then lambda I plus r minus 2 is an eigenvalue of L of G together with minus 2 with multiplicity q minus p. So the adjacency eigenvalues of LG1 is known, so that the distance eigenvalue of LG1 join LG1 and LG2 join LG2 can be obtained, and we can see that the only positive d eigenvalues are 9t minus 6 and 3t minus 6, so that the distance energy is 2 times the sum of positive eigenvalues, so that the distance energy can be calculated. And we can see that LG1 join LG1 is on 60 vertices. LG1 is on 3T vertices, so LG1 join LG1 is on 60 vertices, and that proves our claim. For a very p equal to 60, there exist non-spectral, equi-energetic, distance equi-energetic graphs. Now, similarly, we can prove, or we can have another family, and these are the examples on 18 vertices. D equi-energetic graphs on 18 vertices with energy 48, which are regular. And by a similar argument, we can show that for every p congruent to 1 mod 3 greater than or equal to 10, there exists a pair of equi-d energetic graphs. We skip the proof. Another kind of operation on graphs is the join over union. If G0, G1 and G2 are 3 graphs, then G0 join G1 union G2 is a graph obtained by joining every vertex of G0 to all vertices of G1 and G2, or G1 union G2. In fact, G1 union G2 need not be a regular graph. G1 and G2 may differ in its regularity. Then the distance spectrum of the graph, the new operation, the join over union, is given by minus lambda ij minus 2, where lambda ij's are the adjacency eigenvalues of Gi different from their regularity, and 3 more eigenvalues which are the roots of this cubic equation. And the roots of this cubic equation depends only upon the number of vertices and the regularity of the constituent graphs N0 R0, N1 R1 and N2 R2. So we have this result from this class of D equi-energetic graphs from the join of the union. Let G be any regular graph with least eigenvalue at least minus 2. In fact, there are several regular graphs with the least eigenvalue at least minus 2. And they are line graphs of regular graphs. You take any regular graph, then their line graphs are with the least eigenvalue at least minus 2. The cocktail party graph, complete graphs are all graphs whose least eigenvalue at least minus 2. Then for a fixed n, let the script Pn be the set of all integer partitions of n into parts, each of size at least 3. Then for a partition P is equal to P1, P2, etc. Pk belongs to script Pn. Let Cp be the union of cycles with vertices P1, P2, etc. Pk. Then the graphs K1 join Cp union G forms a set of D equi-energetic graphs. So for a fixed G, K1 join CP union G forms a set of D equi-energetic graphs where adjacency eigenvalues of this CP will change, so that the resulting K1 join CP union G are all non-co-spectral, but they have the same energy. And that follows from this expression, because energy contribution, see for the constituent graph G and CP here, for this G2 and CP, the least eigenvalue is -2. So this term minus lambda ij minus 2 is always negative. So the energy contribution of this resultant graph comes from the positive eigenvalue of this, the roots of this cubic equation. The distance energy contribution is only from the positive root of this cubic equation, and this cubic equation is not varying as n0, r0, n1, r1, and n2, r2 are constants. So this family for a partition P is equal to P1, P2, etc. Pk, K1 join Cp union G forms a set of D equi-energetic graphs. And this is an example on n vertices with n equal to 6. K2, K1 join K2. This is the partition for this is for n equal to 6. We have one partition is 6 itself, and the other partition is 3 plus 3. So this graph is K1 join C3 union C3 union G. G is K2. So this is our CP. CP is the union of the cycles C3 and C3. And for the partition P equal to 6, this is the graph. K1 is here. K1 join C6 union K2. And these two are two equi-energetic graphs. Another operation we proposed in the proposed is the joined union of graphs. Let G be a graph on n vertices, V1, V2, etc. Vn, and corresponding to each vertex Vi, introduce a graph Gi and make every vertex of Gi adjacent to every vertex of Gj whenever Vi and Vj are adjacent in G. And some authors name this as generalized join of graphs. And the resulting graph denoted by G, G1, G2, etc. Gn is the joined union of constituent graphs. And the ordinary join of two graphs G and H is then K2 G H. And we obtained the distance spectrum of the joined union. If G1, G2, etc. Gn are with eigenvalues respectively lambda ij's, then the distance spectrum of the joined union of G1, G2, etc. Gn consists of these numbers: minus lambda ij minus 2 for I equal to 1, 2, 3, etc. and j equal to 1, 2, 3, etc. mi, different from the regularities, and the eigenvalues of this n by n matrix, this matrix. And we call this matrix as auxiliary matrix. And even though G1, G2, etc. Gn varies, this auxiliary matrix remains the same, since the distance between V1 and V2, etc. in these graphs do not changes, and M1, M2, M3, etc. Mn are the number of vertices in G1, G2, etc. Gn. So if we vary G1, G2, etc. Gn accordingly, we can have long distance equi-energetic graphs. And this result was published in Ars Mathematica Contemporanea, authored by Stevanovic in 2009. And this is a family of long distance equi-energetic graphs. Pn C6, C6, etc. C6, and each C6 is then replaced by C3 union C3. And if you consider any other cycles as a C8, then C3, C5, C4, C4, all such combinations can be used to get equidistance energetic graphs. And this is an example for in the case when n equal to 3, P3, C6, 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 here C6, 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 then this is the generalized union or joint union of C6, C6, C6. And the other is 2 C6 and last is C3 union C3. And in fact, one more member among this family can also be exhibited as P3, C3 union C3, C3 union C3, C3 union C3. Okay. Now in our next discussion, we see these 4 graphs. We call this first graph is F1, F2, F3, and F4. Then in 2009, Ramana et al. Proved that if G is any R-regular graph on n vertices of diameter less than or equal to 2, in which none of the above graphs is an induced subgraph. These F1, F2, F3, F4 is not an induced subgraph. Then none of them can be an induced subgraph of LG and diameter of LG less than or equal to 2. And the distance energy of L of G is given by 2nr minus 4r. Surprisingly, depending upon the number of vertices and regularity of G alone. And using this, they and have distance energy. We made in this paper the D spectrum and D energy of the complements of iterated line graphs of regular graphs appeared in algebraic structures and their applications in 2017. That if G is an R regular graph on P vertices with R less than or equal to P minus 1 by 2, then diameter of its complement is equal to 2. And using this observation, we can prove that if G is an R regular graph on P greater than or equal to 8 vertices with R less than or equal to P minus 1 by 2, then diameter of LKG complement equal to 2 for all K greater than or equal to 1. If G is an R regular graph with R less than or equal to P minus 1 by 2, then the diameter of the complement of the iterated line graphs are all equal to 2 for every K greater than or equal to 1. And consequently, the distance energy in case of L2G complement and for any iterated line complement of any iterated line graph, if G is an R graph on P vertices with R less than or equal to P minus 1 by 2, Pk and Rk denote the order and degree of the kth iterated line graph, then distance energy of LKG complement depends upon this initial parameter, the initial parameters of the starting graph G. So considering two non-cospectral graphs with the same regularity and a number of vertices parameters, we can have equi-energetic, cospectral, regular graphs from the family of the complements of iterated line graphs. If G1 and G2 are two non-cospectral regular graphs of the same order with P greater than or equal to 9 and same degree are greater than or equal to 4 with 2r less than or equal to P minus 1, then these two graphs, LKG1 complement and LKG2 complement, forms a pair of non-decospectral d-equi-energetic graphs of equal order, equal number of edges, same regularity, and with energy this. Now we go to fundamental operations on graphs, on two graphs. We have discussed join union, join over union, and now to the Cartesian product. Let G and H be two distance regular graphs on P and N vertices with the distance regularity K and T respectively. And these are the initial paraphernalia of G and H. Then the distance spectrum of G plus H. G plus H means the Cartesian product of G and H are the numbers Nk plus Pt, N mu I, P eta J 0, where 0 is with multiplicity P minus 1 into N minus 1. And mu I and eta J are respective distance eigenvalues of G and H. And this result appeared in distance spectrum of graph composition, Ars Mathematica Contemporanea in 2009. And we can observe from this distance spectrum of Cartesian product of G and H that distance energy of the Cartesian product of G and H is n times the distance energy of G plus p times the distance energy of H. And these are two basic d equi-energetic graphs on n vertices with a diameter 2. These are two distance equi-energetic graphs, non-co-spectral, regular, with diameter 2 on 9 vertices. If we consider any other graph H, then G1 and G2, if we use G1 and G2 as these two graphs, then G1 plus H and G2 plus H, the Cartesian product of G1 and H and G2 with H are d equi-energetic. And another observation is, if G is a distance regular graph of order P and diameter K, and if we define the graphs Gn inductively by Gn is equal to Gn minus 1 plus K2, with the starting graph G0 equal to G for n equal to 1, 2, 3, etc., then diameter of Gn is K plus n, and the distance energy of Gn is 2 raised to n times energy of G plus Np. So the proof is in these few words. Let G be a distance regular graph of order P, and Gn is defined so that Gn is equal to Gn minus 1 plus K2. We start with the G0 equal to G. Then diameter of G is d plus n by repeated application of the observation that the diameter of the Cartesian product of G and H is the diameter of G plus diameter of H. So for the initial graph G0, it is a diameter d. And for the first graph G1 is G0 plus K2. So diameter is d plus diameter of K2. Diameter of K2 is 1. So for the first graph G1 is diameter is d plus 1. Then for G2 d plus 1 plus 1, etc. Inductively we get the diameter of Gn is equal to d plus n. And from the distance spectrum of G and that of K2, and using the distance energy of K2 is equal to 2, we have distance energy of Gn follows this pattern. Ed of Gn is equal to 2 times Ed of Gn minus 1 plus 2 raised to Np. Then this is then a simple recurrence relation, a non-homogeneous linear recurrence relation of the first order. An is equal to 2n minus 1 plus 2 raised to Np. And solving this recurrence relation, we get the general solution as An, the distance energy of Gn, is equal to 2 raised to n into EdG plus Np. And surprisingly, this gives rise to this result that we can construct pair of d equi-energetic graphs of any diameter k for k greater than or equal to 2. Let k be any positive integer greater than or equal to 2, then there exists a pair of d equi-energetic graphs of diameter k. We start with the fundamental graphs. So we start with these two graphs of diameter 2. We form the Cartesian product of these two graphs with K2. Then we get graphs of diameter 3 equi-energetic. Then we use that, form the Cartesian product with the K2. We get graphs of diameter 4 equi-energetic, and this process continues. So that at last we get, for any given k, a pair of d equi-energetic graphs of diameter k. Now the lexicographic product of G and H. The distance spectrum, if G is a graph with distance matrix dg and H an R-regular graph with adjacency matrix A, with distance eigenvalues of G are mu1, mu2, etc., mu p. No specific condition whether G is regular or G is a distance regular. And the ordinary spectrum of G is R, lambda 2, lambda 3, etc., lambda n. Of course, H is a regular graph. then the distance spectrum of the lexicographic product of G and H is given by this set of numbers. So if we choose H as a graph whose least eigenvalue is -2, then lambda j plus 2 is positive, and so that this eigenvalue is always negative. So the energy contribution comes from these numbers. So if we do not change G and vary this H, we can have this family of D equi-energetic graphs from the lexicographic product of graphs. Let G be any graph. Then for a fixed n, let script Pn be the set of all integer partitions of n into parts, each of size at least 3. Then for a partition, Cp be the union of cycles with vertices P1, P2, etc. Pk. Then the graphs. See, we provide examples only in case of Cp. That doesn't mean Cp is the only candidate for this. We can have any family of graph with the least eigenvalue -2. We choose here Cp as union of cycles have the least eigenvalue -2. Okay. Instead, we can have a union of line graphs of satisfying this condition, or union of cocktail party graphs having satisfying this condition, and so on. Then the graphs, the lexicographic product of G with such a Cp, P belongs to the partition family Pn. The lexicographic product G with the Cp forms a set of D equi-energetic graphs. Another operation on graph to get a new graph is the extended double cover operation proposed by Allen in 1980s. G is a graph on vertex set V1, V2, etc. Vp. We define a bipartite graph H with vertex set of H is equal to V1, V2, etc. Vp, U1, U2, etc. Up, in which Vi is adjacent to Ui and Vi is adjacent with Vj's whenever Ui is adjacent to Uj in G. And this graph is known as the extended double cover graph, EDC graph of G. And we proved that if G, we have this result, that G be an R graph of diameter 2 on P vertices with ordinary spectrum, means adjacency spectrum, R lambda 2, etc. lambda P. Then the distance spectrum of the EDC graph of G consists of the numbers these. So using that, in the paper on the distance spectra of some graphs with Gutmann, appeared in Mathematical Communications, we proved that there exists a pair of regular non-D cospectral D equi-energetic bipartite graphs on 24T vertices for every T greater than or equal to 3. We skip the proof. Proof is, if G is you take a cubic graphs on 2T vertices, consider their second iterated line graphs, you form their join F and find the EDC graph of F. Then the EDC graph of these two graphs for two different G1 and G2, such Fs will be equi-energetic. Now we search for D equi-energetic graphs in the family of self-complementary graphs. So we have searched in case of join, lexicographic product, Cartesian product. In all such classes, the answer was positive. There exist. Then now we ask whether there exist D equi-energetic graphs on self-complementary graphs, and this is a well-known construction of self-complementary graphs proposed by Alexander Ferrugia in his MSc thesis. And in fact, that is the joint union of G, G complement, G for any graph G. And in our paper, D equi-energetic self-complementary graphs appeared in Krajichevak Journal of Mathematics in 2009 with Gutmann. We proved that the distance spectrum of such a self-complementary graph P4 G, G complement, G consists of these numbers minus lambda I plus 2 and these two numbers. So from that, we proved that for every p equal to 48t or 24 into 2t plus 1, t greater than or equal to 4, there exists a pair of d equi-energetic self-complementary graphs. There exists a pair of d equi-energetic self-complementary graphs on this p, where p is 48t or 24 into 2t plus 1 for t greater than or equal to 4. The proof is, I'm not going through the proof in detail. First, we showed that there are two 4 regular non-cospectral graphs on 8 vertices. We constructed two particular 4 regular graphs, non-cospectral, on every n greater than or equal to 8 vertices by considering two cases. N is an even number and n is 2t plus 1. We have two different constructions for non-cospectral 4 regular graphs, and using that we constructed self-complementary graphs and proved that those self-complementary graphs are d equi-energetic. Another operation on graphs we proposed appeared in distance spectrum of this product of graphs in ICGC International Journal of Graphs and Combinatorics in 2016 with Dr. Balakrishnan, that there exists a pair of distance equi-energetic graphs of diameter 3 on p vertices for every p equal to 18 plus 2k, k greater than or equal to 1. And the operation is, you take two copies of G1 join G2 and join the corresponding vertices of G2 in two copies of this 2 join. G1 join G2 join with G2 join G1. And we obtained the distance spectrum, and using that we were able to produce a pair of distance equi-energetic graphs of diameter 3 for every p equal to 18 plus 2k vertices with k greater than or equal to 1. In the paper, distance spectrum of corona and cluster of 2 graphs appeared in ICGC International Journal of Graphs and Combinatorics in 2015, jointly authored with Stevanovic. We obtained the distance spectrum of the corona of 2 graphs G and H. If G and H are with these primary conditions, then the distance spectrum of G corona H consists of these numbers. And using this, we proposed this theorem, that G be a distance regular graph for a fixed n. Let Pn be the set of all integer partitions of n into parts, each of size at least 3. Then for a partition P is equal to P1, P2, etc., Pk belongs to script Pn. Let Cp be the union of cycles with vertices P1, P2, etc., Pk. Then the graphs G corona Cp forms a set of d equi-energetic graphs. For example, with a cycle for n equal to 6, this is the corona of C4 with C6, and this is the corona of C4 with C3 union C3. Now these two have same distance energy. Another operation we proposed in 2013, that the subdivision vertex join of 2 graphs. So the subdivision vertex join of 2 disjoint graphs G1 and G2, denoted by G1 vertex subdivision vertex join G2, is the graph obtained from the subdivision of G1 and G2 by joining each vertex set of G1 with every vertex of G2. And we obtained the adjacency spectrum of G1 join G2 earlier, and in a 2000 paper jointly authored with Liu and Dina Scaria, the distance spectrum of the subdivision vertex join and subdivision edge join of 2 regular graphs appeared in discrete mathematical letters. We obtained the distance spectrum of G1 subdivision vertex join G2 consists of these numbers: -2 lambda ij plus r1 plus 1 and minus lambda 2j plus 2 with this. and along with the eigenvalues of the matrix this. And using this, we propose this theorem. Actually, this was not included in that paper. We obtained this, that G be any R regular graph, and for a fixed n, let Pn be the set of all integer partitions of n into parts, each of size at least 3. And for P is equal to P1, P2, etc., Pk, Cp. See, as I mentioned earlier, we can replace this Cp by any graph whose least eigenvalue is -2, and there are several. Just for a uniformity, we use the Cp. The Cp be the union of cycles with vertices this. Then the graphs G1 join subdivision vertex join Cp forms a family of D equi-energetic graphs. And these are two examples with P with n equal to 6. This is in fact K2 subdivision vertex join C6, and this is K2 subdivision vertex join C3 union C3. They are equi-distance energetic. And another operation we proposed in the same paper is the subdivision edge join of two vertex disjoint graphs. That is obtained by joining every vertex of SG1 corresponding to the edges of G1 to vertices of G2. And here also we have a family of D equi-energetic graphs. For every fixed n, if we consider a partition as mentioned before, then the graphs G subdivision edge join Cp, P belongs to script n, forms a set of D equi-energetic graphs. And this is an example. And in I think 5 minutes more, I would like to say a conjecture and some 2 or 3 open problems in this area. So in 2009, we conjectured in our paper Distance Spectrum and Energy of the Composition of Regular Graphs appeared in Applied Mathematics Studies. We conjectured that there exists no pair of non-co-spectral D equi-energetic trees up to 20 vertices. We think that this conjecture is still open. And very surprisingly, when these results are compiled and made for a presentation here, surprisingly we see that many of the classes presented here have equal adjacency energy as well as equal distance energy. That doesn't mean they have the same number for both these. They are equi-energetic with respect to adjacency matrix as well as equi-energetic with respect to distance matrix. So we propose this as an open problem. Characterize those graphs which are equi-energetic with respect to both adjacency and distance matrices. Characterization of equi-energetic graphs with respect to adjacency matrices and distance matrices. Another weak problem is construct families of graphs which are equi-energetic with respect to both adjacency and distance matrices. Another problem we can suggest is, suppose G and H be two equi-energetic graphs with respect to adjacency matrix or as well as distance matrix, or at least with one of them, then any vertex deleted or edge deleted subgraphs of these two graphs G and H are equi-energetic. I think that is a problem to be addressed. I didn't see anyone attempted this problem. G and H are D and H are equi-energetic with respect to a matrix. Then can we characterize those graphs or those edges or those graphs for which G minus E and H minus E are equi-energetic, or G minus a subset of G minus edge set of some K and H minus edge set of some K, where K is a subgraph of G and H. Can we do like this? That is also an open problem. And these are the references and also the references cited in these papers.